I want you to picture a modern commercial airliner. Just imagine you are looking at nearly 500 tons of aluminum, titanium, and, well, jet fuel.
Oh, yeah, it's a massive amount of weight.
Right, and it's somehow just accelerating down a runway and lifting effortlessly into the sky. And I think most of us look at that and see, a triumph of modern manufacturing.
Absolutely looks like pure engineering magic.
But if you strip away the metal, the rivets, the fuel, what is actually holding that aircraft in the air is a concept you likely encountered when you were like 16 years old.
Yep. Sitting in a high school classroom.
Exactly. That massive 500-ton machine is fundamentally just a beautifully executed high school math equation.
It really is the ultimate hidden architecture of our reality.
Yeah.
I mean, the symbols we write on a whiteboard in a geometry or calculus class, they aren't just abstract logic puzzles.
Well, actual tools.
Right. They are the little blueprints for how physical forces interact in the real world.
And that is exactly our mission for today's deep dive. We're looking at a source document titled Day 24 Integrals, Engineering Applications and Code.
Which is such a great breakdown of the topic.
It really is. And the core of this material actually references Chapter 8 of the classic XII Maths textbook, which, for those who might not know, is the national educational standard used by millions of students across India.
A very rigorous standard.
Yeah, and we're going to look at one specific, incredibly powerful mathematical tool from it, the definite integral. So, okay, let's unpack this. Because we aren't going to get bogged down in rote memorization or chalkboard proofs today.
No, nobody wants that.
Exactly. We are going directly to the mechanism of how this concept works in physical space and how it is secretly running everything from the flight you took last summer to the artificial intelligence organizing your life right now.
To do that, though, we have to establish what an integral actually does at its foundational level.
Yeah.
I mean, in mathematics, a definite integral is essentially a tool for accumulating continuous quantities.
Accumulating quantities, right.
Yeah, so if you visualize a function plotted on a graph, like a sweeping line moving from left to right, the integral calculates the total accumulated area that gets trapped underneath that curve.
Ah, the classic area under the curve.
Exactly. But our source document zeroes in on a much more practical application of this, which is finding the area trapped between two different curves.
Which makes sense because, well, that's how the physical world actually works, right?
Yeah, exactly. Nothing is just a single curve floating in a vacuum. Let's say you have an upper continuous function on your graph. We can call it g of x.
Okay, g of x is on top.
Right. And below it, you have another continuous function, f of x. These two lines are sort of weaving across the graph, and they intersect at a starting point, which we call A.
Got it.
And then they intersect again later at an ending point, B. So to find the precise area of the space trapped between them, the mathematics dictate that you calculate the integral of the upper curve minus the lower curve over that specific interval.
Now, the document mentions we find those boundaries analytically by solving for the roots where f of x equals g of x, which sounds, honestly, highly technical.
It does sound intimidating, yeah.
But when I was reading this, I visualized it a bit differently. I mean, imagine two people, let's call them function f and function g, and they're walking across a massive empty field.
Okay, I like this.
And they are walking completely different winding paths. Finding those bounds, A and B, is just pinpointing the exact moments in time where these two people happen to bump into each other.
That's a perfect way to look at it.
Right. So they meet at point A, wander off on their separate curving routes, and then cross paths again at point B.
That analogy maps perfectly to the algebraic roots. You are simply establishing the physical limits of the event you want to measure.
But the integral itself is what measures the space between them, right?
Yes, exactly.
So if we stick with the field analogy, the integral isn't just a number, it's the exact square footage of the grass that gets trapped between their two diverging paths during the time they were separated.
It is. And the mechanism of how the integral actually measures that grass is crucial. Think of a deli slicer cutting a block of cheese.
A deli slicer, okay.
Yeah, to find the total volume of that weird trapped shape on a graph, the integral effectively slices the space between the two curves into infinitely thin vertical rectangles.
Oh, wow. Infinitely thin.
Right. In calculus, that infinitely thin width is called dx. The integral measures the height of each microscopic slice, multiplies it by that tiny dx width, and then sums them all up. It's basically an infinite accumulation of microscopic slivers.
That makes the mechanics of it so much clearer. You're stacking up infinitely thin slices until you have the whole shape.
What's fascinating here is this specific mathematical safeguard built into this process. The source document notes a really vital mechanism. The definite integral neutralizes negative coordinates to provide an absolute geometric area.
Yeah, I actually noticed that in the source. Why do the coordinates need to be neutralized, though?
It comes down to the profound difference between abstract algebra and physical reality.
Yeah.
On a standard Cartesian graph, you can plot negative coordinates all day long.
Right, like -5 on the y-axis.
Exactly.
Yeah.
A curve can dip far below the horizontal axis into negative values, but physical space cannot be negative.
Oh.
Yeah, you can't have negative square footage of grass in your field. You cannot manufacture a negative piece of steel.
Huh. I'd like to purchase -12 square feet of carpet, please.
Right, it falls apart completely in the real world.
That makes total sense.
The universe demands absolute positive space. So when the formula subtracts the lower function from the upper function, when it integrates g of x minus f of x, it corrects for wherever that zero axis happens to be.
It just finds the pure distance between them.
Exactly. It calculates the absolute distance between the two curves at every single microscopic slice, whether those curves are hovering way up in the positive quadrant or dipping deep into the negative one.
So it translates an abstract algebraic landscape into a concrete, usable measurement of physical space.
Yes. Beautifully said.
Which is the perfect bridge into how this actually builds our world. We've established how to trap this absolute area between two curves on graph paper. But our source document takes those curves off the paper and applies them directly to aerospace engineering.
Yeah, and the stakes transition rapidly from just, understanding textbook concepts to ensuring literal life or death structural integrity.
The document points out that integrals calculate the exact cross-sectional area of complex aerodynamic geometries. Specifically, it mentions the airfoil.
Right, the airfoil.
And for anyone unfamiliar, an airfoil is just the technical term for the teardrop-shaped cross-section of an airplane wing.
Yeah, if you were to slice a commercial jet wing perfectly in half from front to back, that profile is your airfoil, and the top surface of the wing has a very specific sweeping curve.
And the bottom has a different curve.
Exactly. The bottom surface is a slightly different, flatter curve.
So the math maps directly onto the physical object. The top surface of the wing is our upper function, g of x, and the bottom surface is our lower function, f of x.
You are looking at a living integral. I mean, the leading edge of the wing, where the air hits, is boundary A.
Okay, I see it.
And the sharp trailing edge at the back is boundary B. The total absolute area trapped between those two continuous curves determines the internal volume of the wing structure.
Which is crucial, right?
Incredibly crucial. That tells aerospace engineers exactly how much fuel the wing can hold, which dictates the maximum weight, which then dictates the necessary thrust.
Wow, all from that one area calculation.
And beyond internal volume, the exterior geometry of that trapped area governs the aerodynamic flow. It dictates the lift-to-drag characteristics of the entire aircraft.
And it isn't just the wings. The source document also brings up aerospace propulsion, the jet engines driving the whole system forward.
The propulsion systems, yes.
It mentions that the area under a pressure-volume thermodynamic curve equals the total work done in jet engine combustion cycles.
Thermodynamics relies heavily on this logic. Engineers use a graph plotting pressure on the vertical axis and volume on the horizontal axis.
Okay, pressure and volume.
As a jet engine goes through its stages like intaking outside air, compressing it tightly, combusting the jet fuel, and then exhausting that high-speed gas, the changing relationship between pressure and volume traces a continuous loop on that graph.
So I understand that the integral calculates the physical area inside that loop, but the document says that area equals work, or measurable energy. How does an area on a graph suddenly become mechanical energy?
It's all about the units.
Yeah.
Let's break down the units, because this is where the physics gets truly beautiful. Pressure is defined as force divided by area.
Force over area.
And volume is defined as area multiplied by distance. So when you calculate the integral, you are mathematically multiplying the axis by the x-axis.
Which means multiplying pressure times volume.
Right. And when you do that, the area units cancel each other out, and you are left with force multiplied by distance.
Wait, and force times distance is the literal physics definition of work.
Precisely. The geometric area trapped inside that thermodynamic loop on a piece of paper is a direct one-to-one calculation of the mechanical energy that the jet engine will produce in the real world.
Here's where it gets really interesting. Does this mean that every time you board a commercial flight, the actual physical shape holding you in the air and the engine thrusting you forward are just perfectly executed integral equations?
If we connect this to the bigger picture, engineering is simply mathematics made manifest. We see titanium and carbon fiber, sure, but the structure is entirely made of logic.
It's just mind-blowing to think about it that way.
If an engineer miscalculates the bounding area of that air-cooled design, the lift-to-drag ratio breaks down, the plane simply cannot overcome gravity.
It won't fly.
Exactly. And if the area under that pressure volume curve is miscalculated during the design phase, the combustion cycle will fail to produce enough mechanical work to propel the mass.
So we use integrals to measure massive physical objects like jet wings. But the deep dive source takes us into a completely different domain next. We move from aerospace to the invisible realms of electronics and computing.
Yeah, the integral isn't just measuring physical space anymore, it's measuring data and time.
We are shifting from accumulating physical geometry to accumulating invisible physical forces.
That's exactly it.
The document discusses electronics engineering, specifically how integrating a current time curve yields the total electric charge stored in a capacitor.
Right, think of a capacitor in a circuit board as a sort of reservoir storing up potential energy, the electrical current. The actual flow of invisible electrons, it fluctuates over time.
Like it might surge initially, taper off, and spike again.
Exactly. And if you plot that fluctuating flow rate on a graph against time, you get a curve.
So the infinitely thin deli slices we talked about earlier. In this case, each slice is a tiny fraction of a second.
A tiny fraction of a second, multiplied by the exact flow of current at that specific microsecond.
Wow.
When the integral sums up all those slices of time, it provides the exact absolute quantity of electric charge that has accumulated in the reservoir. I mean, you cannot see an electron, but the mathematics can perfectly quantify millions of them accumulating over milliseconds.
That's incredible. The source also gets into how this applies to alternating current or AC signals. Basically, the power coming out of our wall outlets.
Right, AC power.
It states that calculating the root mean square, the RMS voltage of an AC signal, relies on evaluating the area bounded under a squared waveform curve. Now, I have a question about the mechanism here. Alternating current constantly swings up into positive voltage, then dips down into negative voltage.
It traces a perfect sine wave, right? Like above and below the zero axis, yeah.
Yeah. So if you just took a basic average of that wave over time, the positive peaks and the negative valleys would cancel each other out, giving you an average voltage of 0.
Which obviously isn't true.
Right, because AC power lights up our houses, it's not 0. So the document says engineers square the waveform curve first to make everything positive and then integrate it.
Yes, that's the standard method.
But earlier, we talked about just subtracting the lower curve from the upper curve to neutralize negatives. Why are we squaring the whole wave here instead of just taking the absolute value and flipping the negative dips upside down?
Ah, that is an excellent catch. Why not just fold the negative part up? Well, the reason engineers square the waveform is due to the strict requirements of calculus itself.
Okay, how so?
If you just flip a negative dip up, you create a sharp, jagged point at the zero axis where the wave suddenly changes direction. In calculus, a sharp point is non-differentiable. The math literally breaks down because there's no smooth slope.
Ah, so you can't smoothly slice it with our imaginary deli slicer if there are jagged, broken angles.
Exactly. The math requires continuity. By squaring the function, you preserve the smooth, continuous nature of the curve.
That makes a lot of sense.
And furthermore, squaring naturally gives heavier weight to the extreme peaks of the voltage wave, which physically aligns with how power actually dissipates as heat in a resistor.
Oh, that's elegant.
Once you integrate that squared curve to find the total area, you divide it by time to get the average, and then you take the square root of the whole thing to bring the units back to normal voltage. That is your RMS. It's just a mathematically flawless way to measure a fluctuating bidirectional force.
The consistency of the logic across entirely different scientific fields is amazing. But I want to move to the competing and machine learning section of the source document, because this is where I found myself wanting to push back a little.
Oh, really? You were referring to the ROCAUC metric in artificial intelligence, right?
Yes, the area under the receiver operating characteristic curve. Quite a mouthful. The document notes that machine learning algorithms use this bounded area as a single scalar metric to evaluate how well a model classifies distinct data.
Basically, how good the AI is at telling two things apart.
To give that some context, the ROC curve plots the true positive rate against the false positive rate. Imagine a medical AI trying to detect a disease. The curve maps out how often the AI correctly flags a sick patient versus how often it falsely alarms on a healthy patient across every possible sensitivity threshold.
Right. And a perfect AI would have an area under that curve of 1.0, while an AI just randomly guessing, like a coin flip, would have an area of zero point 0.5.
Exactly. But here's my issue. You have this massive, highly complex algorithm making millions of nuanced decisions to generate that curve. And the ROCA you see just integrates the area underneath it and spits out one single number, a scalar metric.
Usually a decimal, yeah, like 0.85.
To me, that feels incredibly reductive. It's like taking a university student's complex, messy four-year academic journey. They failed a class in sophomore year, they rallied, they wrote a brilliant senior
A
thesis.
lot of ups and downs.
Right. That entire journey is a rich curve of nuanced data. And then the university integrates it into a single flat GPA, a 3.2. By compressing all the rich data of a machine learning model's behavior into a single geometric area, don't we lose the vital nuance of how the AI is actually making decisions?
This raises an important question, and frankly, it is a debate data scientists have constantly. You are entirely correct that compression destroys nuance.
See, that's what I thought.
A curve tells a complex behavioral story. A scalar area is just an executive summary. However, in the context of modern software engineering, that level of compression isn't a flaw. It is a feature required for velocity.
But wouldn't an engineer want to see the nuance to know where the AI is failing?
At the end of a project, yes. But consider the development phase. A machine learning engineer might set a computer to automatically train 100 different variations of a classification model overnight.
Okay, that's a lot of models.
The next morning, they need to know which one of those 100 models performed best overall. If the engineer has to manually review 100 complex ROC curves, analyze the true positive versus false positive trade-offs for every single one, the development cycle completely stops.
Oh, I see. It would take forever.
Right. By integrating the curve into a single area, the system provides a mathematically sound instant ranking system. Model A scored 0.92, Model B scored 0.88.
So it balances the deep underlying complexity of the statistical math with the practical need for operational speed.
Exactly.
It sacrifices the deep story for the ability to iterate quickly. I can see why that's necessary in tech.
And just to briefly touch on another computing application mentioned in the source, computer graphics.
Oh, right, rendering engines.
The physics of light are simulated using continuous surface integration. When you see a hyper-realistic reflection on a wet street in a video game or a CGI movie, the rendering engine, often using ray tracing, is constantly running integrals over the geometric surfaces.
To figure out how the light bounces?
Yes, to calculate exactly how millions of individual photons would scatter, bounce, and accumulate in a virtual camera lens.
So whether it is the physical shape of a jet wing lifting you into the sky, the electrical current lighting your home, or the glare on a virtual car, it all comes back to finding the trapped area between curves.
It really does. It's everywhere.
Which brings us to the final section of our source document, bringing it to life. We have covered the pure theory and the massive real-world applications, but how does a modern student or working engineer actually interact with this today? We are moving from the textbook theory to actual execution.
The document highlights two specific approaches. The first is highly visual. It's an interactive conceptual tool.
Yeah, it describes a visualization where users can manually alter the algebraic coefficients of a quadratic parabola, a U-shaped curve, and a straight intersecting line.
Right, using sliders.
As you drag those sliders to change the numbers, the tool dynamically shifts where the line cuts across the U-shape. You watch the intersection bounds shift, and you see the total trapped area shrink or grow in real time.
Which is brilliant, because it removes the barrier of doing the calculus by hand. It allows the brain to intuitively connect the abstract algebra directly to the changing physical geometry.
But the part that really stood out to me was the practical code implementation. The source details a Python script used to calculate this trapped area automatically.
Yes, the Python script.
It breaks down the libraries. It uses SIMPy for the analytical calculations, so handling the abstract algebra NumPy for the hard numerical number crunching, and matplotlib to draw the graph on the screen.
Those are the standard powerhouses, yeah.
So what does this all mean? When I read the code, it uses a specific function from matplotlib called fillBetween to highlight the trapped area. Despite all this intimidating high-level Python library jargon, fillBetween is essentially doing the exact same coloring inside the lines work that we did with crayons as kids.
Huh. That's a great way to put it.
The math just finds the borders and Python colors in the grass.
Coding often feels like deciphering a dead language.
Hmm.
But underneath the sophisticated syntax, it is usually just automating our most basic spatial intuitions.
Totally.
But there is a specific constraint about this code implementation mentioned in the source that I believe is the most valuable takeaway for anyone trying to learn a complex skill.
Oh, you were talking about the time limit it imposes.
Yes. The document notes that the practical Python code adheres to a strict 20-minute daily boundary constraint.
I found that fascinating. If you are trying to learn something as dense as applied calculus in a programming language, why would you limit yourself to just 20 minutes? Wouldn't you want to study for hours?
You'd think so, but it is entirely about managing cognitive load.
Cognitive load.
The source states that this time constraint keeps the user's focus exclusively on the mathematical logic and the physical behavior of the area calculation. In software engineering, there is a notorious trap known as tutorial hell.
I've definitely heard of that.
A learner sets out to build a mathematical model, and 3 hours later, they are fighting with software dependencies, debugging a user interface, or arguing with a mismatched library version, and they've completely forgotten the calculus they were trying to learn in the first place.
Ah, they get lost in the architecture of the software and miss the actual lesson.
Exactly. By forcing a 20-minute daily boundary, the script must be standalone, modular, and optimized for immediate execution, like running it in a Jupyter Notebook environment.
Keep it simple.
You strip away all the software engineering bloat, you define the upper and lower functions, you calculate the bounds, you use fill between to color the area, and you execute. The limit proves that when mastering complex, intimidating technical skills, endless grinding is often counterproductive.
You integrate the knowledge far more effectively in small, intensely bounded areas of focus.
Small, bounded areas of focus.
I think the math has permanently altered my vocabulary.
It happens to the best of us.
I think it has altered how I look at everything around me. So for you listening, I want to take a moment to recap the journey we've just been on. We started with what might be the most intimidating visual imaginable. A dry, insert math textbook covered in alphabet soup and stretched out S symbols.
A nightmare for many, yeah.
But by peeling back the jargon and understanding that a definite integral is simply a tool, a deli slicer for measuring trapped accumulated space, we uncovered the mechanics of the modern world.
But it's all corrected.
We saw how measuring the exact footprint of space between two curves dictates the shape of a wing that can carry 500 tons through the sky. We broke down how multiplying pressure and volume directly calculates the mechanical energy of a jet engine.
Work and energy.
We looked at how it measures the invisible flow of electrons to provide reliable AC power to your home, and how it compresses millions of data points into a single metric to train the artificial intelligence of the future.
Right.
And finally, we saw that you can recreate all of this logic yourself using just a few lines of Python code, as long as you keep your focus strictly bounded.
Moving from the abstract chalkboard to the physical reality of human achievement.
And it serves as a powerful reminder. I mean, it is incredibly easy to feel overwhelmed by information overload and complex technologies today. But when you break the systems down, the modern world operates on foundational, logical rules. The airplane isn't magic, it is a solved equation. The artificial intelligence isn't an alien brain, it is an accumulation of curves.
And as we conclude this deep dive, going back to that foundational idea of the integral as the ultimate tool for accumulation, we'll leave you with a final thought to mull over.
Okay, I'm ready.
We have established today that the definite integral perfectly measures the accumulation of continuous physical forces, whether that is electrical charge accumulating over time or thermodynamic pressure expanding in an engine.
Right.
But if this mathematical tool is universally applicable to continuous inputs, could we theoretically design a mathematical curve to measure the accumulated sum of abstract human concepts?
Oh, wow.
Could we one day write an equation to calculate the exact area under the curve of societal knowledge over centuries? Or plot the continuous fluctuating curve of a human life, integrating the total accumulated experience from the lower bound of our birth to the upper bound of our final days?
That's a heavy thought.
What would the true absolute area of that trapped space look like?
Well, that is a deep dive for another day. Thanks for listening.